everybody. So my name is Costas, for those of you who don't know me. And I thought I would just give a couple of lectures on a hopefully relatively simple topic, which has to do with solitons in the BPS bound. Now, those of you who've studied supersymmetries, perhaps string theory, and other aspects of quantum theory, have probably heard this word quite often being uttered, so BPS, and it usually it involves many things at different levels, and it means different things to different people and in different models. But one of the fundamental things about it, at least at some classical level, is that it has to do with situations when, despite the nonlinearity of whatever equations you're looking at, you're actually allowed to linearly superpose solutions. And so that's something that is perhaps quite unexpected. And I just thought, let me go back to basics, and there will be very little supersymmetry in this talk. But let me just say a few things about how this bound is originally derived. So what are these BPS states in very simple systems, and connected to the framework where this was originally discussed, which is that of solitons. So the plan of these talks is, so today I'm going to say a few things about solitons in simple systems, which will be 1+1 systems like the KdV equations and Sine-Gordon, which I will introduce. Hopefully some of you will have seen some of these systems before, because they are quite common in studies of not only solitons but also in studies of integrability. Because as we will see, although it won't be the focus of my talk, these equations have some very interesting integrable property. So after that, I will discuss the Bogomolny bound in simple systems, and hopefully then move on to the 40 case, or the 3+1 case, and the study of monopoles, where this actually becomes a bit more useful. It is already useful here, but this will be closer to the context that perhaps some of you might be familiar with in the study of case theory, and perhaps also history. So there will be references given in between, and the tutorial that I plan to do is basically just working on some of the details of this bound and of solitons in the Sine-Gordon model. Okay, so I will guide you through that after. Okay, so let me start. And okay, sorry, I forgot to mention one thing. Of course, the reason for these very special properties of solitons, and in particular of cases where the BPS bound is saturated, has a lot to do with topology. And by topology, I just mean something very simple. I just mean that our field configurations are considered, two field configurations are considered equivalent if they can continuously be deformed to each other. If to deform a field configuration to another, you have to go through some infinite energy sort of configuration, then these are topologically distinct configurations. So I will have more to say about this, although don't expect a general discussion about topology. It will be very focused on the physical problems in hand. But it will be very crucial to connect, and these are the kind of solitons we're looking at, to connect to the topology and topological sectors to the kinds of solutions of differential equations that we're looking at. Okay, so this is not really supposed to be understandable at this stage, but we'll hopefully get there. So let's go back to the very beginning, and let's see what was the first soliton-like equation or a system that people were looking at. And traditionally one goes back to the observation of solitary waves by Scott Russell in 1834. in Glasgow. So what Scott Russell observed was that he was riding his horse along the canal, and he saw a perturbation of the water in the canal, and that perturbation, that wave, somehow inexplicably was moving on without dispersing, so without losing its, without spreading out as waves typically do. And he followed it for a couple of miles, and eventually until he kind of lost it. But he was kind of fascinated by the idea that there could be such kind of wave solutions to a system where one would expect some dissipation to occur. So the original situation was of a soliton, or what we will call a solitary wave, is some kind of solution like this. So this is the height of the water that I'm plotting here. This is the water in the canal, and this is a configuration which moves in a dispersionless way, without spreading out. Now, this was studied by several people after this, but the equation that we take as the one that describes waves in shallow water is the Korteweg-de Vries equation. Okay, formulated in this way in 1895. And now they're using two kinds of formulations of it, but the standard way of writing it, or the more or less standard way of writing this equation is this. 6u du over dx plus the third derivative. Now u, you can think of it as the height of the wave. Okay? So it's related to how high or deep, because these objects are also, these solutions also exist for you describing the depth rather than the height. So this is u, which is a function of x, or this, but also time. Right? So it's a function of these two variables. So we're 1 plus 1 dimension. So how can such a system, one can ask, so this kind of equation, which is summarized as KBV, does it admit solutions which behave in this solitary wave manner? So how is that possible? You can notice, of course, a couple of things. One is that it has a third derivative term. Another thing is that this here term is nonlinear. This is a nonlinear equation, since this term is quadratic in the function u. So this is an interesting partial differential equation, and a lot of effort has been expended in the theoretical, sort of mathematical physics community to understand all the possible solutions of equations like these. It can be generalized in various ways.
Simple intuition as to why this particular form.
How it was derived, I'm not really going to be able to say why this. Why exactly this appears when you look at shallow waves. I'm sure I can give some solution in detail. But it also appears in different systems as well. It's not. I think there's some relatively universal properties. So how do you? Okay, let's study this and see what we might expect from solutions of this equation. Okay, just to see how we actually get the solitary waves. It's convenient to study, well, we're going to study various limits of this. One limit where we ignore the nonlinear term and we focus more on the linear terms, and another one where we ignore these higher order terms and we just focus on the nonlinear term. And what we're going to see is that the behavior in those two cases is very different, but if you add both together, they kind of balance out to give us this nice, interesting solution. So to do this convenient, and here I'm following a book on solitons by Johnson. It's an old book, but it has some nice introduction to the Korteweg-de Vries equation. It's convenient to actually do a little change of variables. There are many formulations of KTV. So you open a different book and you're going to find a different way of writing it. One slightly different way of writing it is, you can just change your variable. This just will make our limits, it doesn't change any of the physics, just makes our limits a bit more convenient. So do a transformation like this, And we'll find an equation like this, du over dt plus 1 plus u du over dx plus the third derivative is 0. So it's basically just a small transformation which added this. The factors of 6 cancelled out, but here there were 2, so that cancelled out this extra. So I'm going to also introduce the notation, just to avoid writing all these derivatives, that u dot is the time derivative, and u prime is the space derivative. So the first thing we're going to do is linearize. Okay. So linearize means let's ignore the nonlinear part and just write the linear equation down. So this equation is going to look like u dot equals u dot plus u prime plus u triple prime is 0. And now let's focus on, because it's a linear equation, so now we can try to use our usual, let's think of a single frequency wave, a propagating wave that we want to try to see whether it's, what we have to do for it to be a solution for this. So everybody hopefully is familiar with how we write down traveling wave solutions in normal wave physics. So you'd write something like u equals e to the ikx minus I omega t. And okay, is everybody, do I need to explain anything about this? So this is our usual sort of wave which has one particular value of the wave number and a given frequency. Okay, so it moves with a given energy and it has a particular momentum which is related to its wave number. Okay. And everything is totally classical here, of course. I'm not doing anything special. Okay, so let's see. Let's plug this into the equation and see what does k and omega have to be for this to be a solution. So this is, of course, something that you've done hopefully quite a few times before. So what we'll find is, so plug it in. From the u dot term we get minus I omega. From the u prime we're going to get I k, and from the triple derivative you're going to see this is going to act on this 3 times, so it's going to give us a term like minus I k cubed, because there are 3 i's, so we get times u is 0. So what we find is, okay, let me write it here. We find the dispersion relation which looks like this: omega equals k minus k cubed. If this equation is true, so if the angular frequency is related to the wave number in this simple way, then this is a solution. Okay, so we solve this in the linear limit. Okay, but now what does this mean? Okay, so what does this dispersion relation mean? I think you're all familiar with wave and group, phase and group velocities. So, and if you're not, I'll just remind you what the idea is. So, whenever you're given dispersion relation, which essentially it's kind of an energy momentum relation, just written in these kind of more angular variables, but it just relates your energy, which is, in quantum mechanics would be h bar omega, your energy to your momentum, where momentum is h bar times k. Whenever you're given a relation like this, you can derive 2 kinds of velocities for your system. Right? One has to do with the velocity of a given phase. So if I give you a particular wave packet, and then I ask you how does this wave packet behave, well, there's 2 things you can do, right? You can find the phase velocity. Okay, and the phase velocity here is going to be qp, vp. Let me try to use v because that should not confuse it with this u here. But vp is going to be omega over k. You can go back to your sort of second year waves book if you're not familiar with these formulas. And this is going to give us 1 minus k squared. Now let's look at the group velocity. And then you find the group velocity, which is now, does anybody remember the formula? There's not omega over k, but something similar. The derivative of omega over k. Right? And in this case, this is going to give you 1 minus 3k. Okay. Now, what is the meaning of these things? A phase velocity is, of course, within this wave packet is created by adding together many possible oscillatory solutions like this, right? So if you try to follow a particular phase here, the phase velocity is how that particular phase is going to move. The group velocity is the more physical quantity, which tells us how this envelope. Okay, so everything should be kind of inside this envelope, if I were to draw it correctly. But it's not about how the individual phases inside the envelope move, it's about the full envelope that should be moving with the group velocity. Okay. But now, as you can see, because there's this disparity, and because there's a dispersion relation, that means that different frequencies. Well, by the way, let me also say that if you have a wave packet like this, you can associate the size to the wave packet, which is of course proportional to something like 2 pi over the wave number, where we recognize the somehow signal theoretic version of Heisenberg's uncertainty relation. Right? This is uncertainty for Fourier transforms. So basically, that means that if you have something which is pretty localized, so its delta x is very small, it should have a large wave number and the other way. So what you find though is, okay, and of course a very long wave will have k equals 0, so that's something which is very spread out. But what you find is, because of the different kind of phases inside, and because the shorter or the longer your wave is, that its velocity is different, because you see this velocity will depend on k, that such a wave packet will tend to disperse. Right? So some of the frequencies are going to be moving faster, some of them are going to be moving slower. So if you were to let this go for a while, then this would tend to kind of disperse, because that's how the different frequencies spread out. So this is the normal behavior for a linear wave equation that you've seen many times. That's why we call this a dispersion relation. It's related to how this thing disperses and spreads out. Again, stop me if I'm sort of assuming too many things, but hopefully this is relatively clear that there are different phases that you need to put in to make a wave packet, and that will lead to different velocities, and this thing, of course, the group velocity will not change, but the dispersion will change, so the size delta x will then change. Okay, and now the reason for this dispersion actually is, if you think about it, like the difference between the phase and group velocities comes from this k cubed term, which comes from this. So that triple derivative is kind of what is essentially driving the equation or the solution to disperse. So now let's do the opposite thing. So remember, here I took this equation and I linearized. Well, now let's forget about this term, okay? Which you can justify if you think of slow moving. So not slow moving, but the gradient being very small, so you can get rid of this term, and let's focus on the nonlinear term. Just keep the KTV equation. Oh, all right. So if we now look at if we ignore the triple derivative and we look at the nonlinear term, what we're going to get is some equation like this. So now I'm keeping the nonlinear, and it's going to look something like u dot plus 1 plus u times u prime is 0. Now, this is perhaps not the most obvious differential equation to solve, but of course it is much easier than if that extra term was there. And you can easily convince yourselves that if you take u, and I'm going to leave this as an exercise that we can look at in the tutorial, just due to lack of time. If you take a function of x minus 1 plus u of t, so assume that your solution takes this form, this is the same u, and now plug this into here. You're going to have some derivatives on u, on t, on the prime is going to have derivatives on x and on u, but it turns out that this is actually a solution. There's a method behind this called the method of characteristics, which I'm not going to go into, but once you have it, it's easy to plug it in and see the system. Where, of course, to get this right, you should remember that these are partial derivatives, full derivatives, so that will affect what you actually apply. But given this, what this tells us is that the velocity v, because look at this, right? So this is telling us if you choose this to take a particular value, this thing is telling us what the velocity is, right? So let's say you want the phase where this is 0, so you choose x equals 1 plus u times t. So the velocity is 1 plus u. So I'm just looking at x equals 1 plus ut, and that tells me the velocity is 1 plus u. And what does that mean, though? It means the velocity is proportional to the amplitude of the wave. Because remember, u was the amplitude. It was like how high the wave was. I deleted the picture, but it did. So if you take a wave like this, and this is u, and this is I guess this is x, and you look at a point here. Well, the velocity here of this particular point of your solution, which is 1 plus u, is going to be higher than a point here. Right? So it all has velocity, so the whole thing is moving to the right. But the velocity up here is actually higher than the velocity down here, because u is higher. Okay? And we claim the velocity proportional to 1 plus u. That means that as you move forward in time, these points are going to start concentrating this way, and you're going to get something like this. Okay? And it'll actually turn to localize. The more you move forward in time, because these points have a higher velocity, actually it's going to start localizing until it reaches a point where you get a snap, something like a sonic boom. Because of course this cannot go on forever. You have this thing concentrated, becoming more and more kind of singular. Eventually you get some kind of breakdown of the solution. So what I'm claiming from this is that, and again, we can do this a bit more carefully. I'm just trying to give some intuition that the nonlinear term actually tends to want to concentrate your wave. Of course, my picture could have been a bit better, and I would have made it more concentrated. So the nonlinear tends to concentrate it, while the linear part tends to disperse it. Okay, and the solitary wave is the place where you have this precise balance between the linear and the nonlinear. So that's hopefully a relatively intuitive way of seeing why there are two different behaviors in this equation. If you put them both together, you might hope that you can get something which neither disperses, not sort of concentrates, it just moves with a constant profile and is stable for its whole. So, yes?
Yes, and so when we made the transformation from u going to minus u plus 1 over 6, we could have changed the 1 to any number, and it would have still...
Sure, yeah. There are actually, I can show you the more general forms that people write, but there are actually in the KTV equation there are like 6 or 7 like constants that presumably different physical systems satisfy, but the overall behavior is the same. You just change those constants, putting them to 0, whatever doesn't actually.
So then what constrains it to being positive? I mean, it could have been negative and then the velocity at the top is less.
Yes, actually we could have done that. There is a form of the KdV equation which has a minus. And all it tells us is that instead of looking at a height of a wave, we're looking at the depth of the wave. Okay, so you can have different KdVs depending on your situation. But actually what I'm going to do now, I'm going to be finding negative heights. So it will be like a depth wave rather than a height wave. But by doing exactly what you said, just choosing a different constant in front, minus or plus, would change it. But the overall physics does not change that much by doing this. But it's important to be careful about it. Okay, so I'm going to look quickly for now that I've tried to argue that there should be a solution, let me actually find it. Okay? Let me try to find a solution to KdV which satisfies what we expect from this sort of solitary wave discussion. Okay, so basically Scott Russell's observation of this soliton. So let me write the equation again, but this time in the shortened form and in the original way that I had it. Something like this. And now we want to find a solution which has fixed shape and size. Because we expect this to be there, so let's find it. And the way one can approach this is write this general height or depth function u as some function of some new variable y, where my y is x minus ct. C is the velocity, it's not the speed of light, it's just the velocity of the wave in the speed. Now this is very crucial what I did, right? I mean, I connected x and t in this particular way. I'm saying my solutions can only be of this type, right? Because this is the type that I want. This is something which moves with constant velocity, right? Unlike, the solutions we had here, where there were two different velocities and wave packets. This is supposed to move with a constant velocity, and it's supposed to not, because it should always have this form, it's supposed to not disperse. So let's see how we do it. Now I'll do a couple of calculations, but hopefully they will be not too difficult to follow. So you can take this and plug it in this equation. What you find is minus. Okay, and please stop me from doing anything. Zero, where now prime means d over dy. So basically you see that when you take, for instance, the time derivative, I can write that as minus c times the derivative with respect to y, which is this function. And similarly for that. Any questions about what I just did? I just plug this in because I want to find the solution. Now I'm assuming it's an ansatz that my solutions of this type. I think you heard the word ansatz many times today. So I'm just now plugging it in and finding whether I can satisfy this answer. Okay, so now let's try to slowly solve this. I can put this on the left, so f triple prime equals cf prime plus f prime, and I can integrate. Okay, so let's integrate both sides over dx or dy. Again, I'm going purposely a little bit slow here, but I think it's kind of nice to actually see how these functions that we're discussing come out. Okay, so you can integrate and you get something like f double prime equals cf, because here there's nothing to do. Here there is a little bit more work, so this is 6 times the integral of f prime dy, plus, you can add the integration constant, just integrating, and here, this you can write by realizing that this can be written as d over dy of f squared, if you are the half. So now I'm going to put a 3 here, keep the integral. Was this transition clear? I mean, this is going to give me a factor of 2 times f prime. But now you see that I have a total derivative term, so I can also easily integrate. And I'm going to end up with f double prime equals cf plus 3f squared plus I'm not fully done yet. There's one extra step that I would like to take. Now I need to integrate again. I would like to integrate this again and get something for f prime. Right? So for my first derivative of my function f. Now I have a second derivative. That's not directly obvious how to do it, but there's again one of these nice tricks that we can apply, which is to rewrite this as some differential over f instead of y. And the way to do it is to write, to realize that this equation holds. So if you have this over if you have this kind of derivative, which is d over df of df over dy squared, that you can write as 2 d over dy df by applying the chain. Right? So you get dy, and you get something like this, and this is equal to 2. Again, maybe this went a bit fast, but again, these are things that we can discuss in more detail in the tutorial, but this is actually a true equation. Just an application of the chain rule. And from this, we can now rewrite this term, f double prime, as 1/2 of this, and take the f on the other side, so that we get something like. So there's a 1/2 times df prime squared df equals that thing on the right hand side, so 3f. Sorry, I changed the order slightly. Now you can integrate with respect to f. And what we conclude is 1/2 f prime squared equals f. Sorry, there was a square somewhere. This was a square. So this is f cubed plus this is a 1/2 cf squared plus af plus some new constant d. So that's one more equation that we have for our function. And now we can, at this stage, of course, we can look for many different kinds of solutions, depending on our integration constants. So the constants are going to tell us essentially how does this solution behave at plus and minus infinity. We can choose the simplest just to illustrate how these things look, where we choose the boundary conditions that we want f and f prime and f double prime to go to 0 as y goes to plus minus infinity. So that's a requirement that we normally also ask in field theory from our fields, that because we would like some kind of bounded energies and all that, and we would like them to be going to 0 far away. This is not necessarily going to be a requirement for us when we go to the monopole solutions and similar similar setups, but at least now, just for simplicity, let's do this. And what we find is, of course, that if you want this to happen, like look at this, then you'll find, say, if f prime has to go to 0, f has to go to 0, then you find that b has to be 0. From this one, you find that a has to be 0. So these terms have to actually vanish, not at infinity, but always. If you want this one, because there is no f here, so this should be just true. That allows us to simplify our life even more, and then we get something like 1/2 f prime squared equals f squared f plus c over 2 equals 2. Which is actually not too difficult to integrate, right? So this is df over dy. We can leave the dy on one side, take the df on the other side, and we would get something like y, which is the integral of dy, should be the integral of df. Okay, let me just write like df dy. Okay. This is just an identity, I'm not doing anything. df dy is this. Okay, what's inside here? So you can quickly see that what we get is df over f 2f plus the square root, because of course this was squared, so you need to first take the square root, and you got rid of something. Now again, this might not immediately strike you as the easiest integral in the world, but it's actually a known, a relatively easy integral. So those of you who have your laptops and you have something Maxima, Maple, mathematical laptops, I mean, just try it, and then invert it to find f as a function of y rather than y as a function of f. And what you'll end up with, hopefully, is that f of y is minus c over 2. The hyperbolic second squared, called square root of c over 2, y minus y. Okay, y0 is an integration constant that we have. I cannot ignore here, but there should be one integrate. Okay, so this is our first solitonic kind of solution. I will soon sort of stop calling this a soliton. I will only call this a solitary wave, and I'll explain what the distinction is. But now, if you remember what the second hyperbolic is, does anybody know how this function would look like? So first of all, what is the cosine hyperbolic? The cosine hyperbolic of x, that is, yeah, so e to the x plus e to the minus x over 2. So where does it have its minimum? X equal to 0. And that value is 1. So this is 1 at x equals 0. And then what happens as you move away from x equals 0? Does it increase? Does it decrease? Okay. Because if you go towards positive numbers, then this takes over, right? So this is going to be an exponential increase. If you take negative numbers, this is going to be taking over, and this is going to vanish. So if you were to plot this, it would look something like this, right? So it starts from not 0, but from 1, and it will increase. Now, now the second is of course 1 over this, right? And it's squared, so if you were to plot a function like this, how would it look? Yeah, where would be the maximum would be where? So suppose I were to plot my y, this is my y0 at the middle. This would have a maximum here because that's where the cos has the minimum. Right? So, and that maximum would be somewhere here. Of course, that depends on the values here. And then what's going to happen? It's going to fall off. And actually, it's going to fall off really fast. It's the square of something which is falling off exponentially. So this doesn't do it justice. This looks like Gaussian, actually falls much faster. So this is a localized solution. This is a lump of energy density, if you like. You can calculate what energy density is. And it moves in time, because remember y was x plus or minus yt, minus ct. So it moves with some velocity. And there are different things that you can say about it, but okay, I think my time is kind of running out and I want to introduce a few more things. But you can look at the amplitude, for instance, which is defined by this, like how big it is, that's proportional to c. You can look at the width. Okay, so the width you can define in some way like that. That's proportional to the square root of c, and you can look at various other features of this solution. But the important thing is, of course, that we actually managed to explicitly solve. Okay, of course, I took a few shortcuts here and there just to, and of course, doing this integral, I would not have directly been able to tell you the answer without Maple or something. But you can relatively easily solve it and give me the solution. So remember this, the second hyperbolic square actually is a feature that arises very often in these kind of problems. Any questions about what I did so far? Okay, so this was more or less all I have to say about the KBV equation, because now for the tutorial we're going to be doing something slightly similar, but for a more interesting, version of a more interesting system, which is the Sine-Gordon equation. And the reason about more interesting is because it's something that has a more of a particle flavor about it, so you will feed into the discussion we're going to do on Thursday on monopoles slightly better. Alright, so let me now, because I think my time is actually running out and I might not reach the Bogomong amount today, but I think it's important to stop here and give a couple of definitions. Now, what actually a soliton is a slightly fuzzy concept in the literature. Right? So there is no sort of uniquely accepted name, or even if there is, people don't follow it. Okay. So what we just discovered here, which describes this solitary wave in some narrow channel, like shallow water, you would find it called a soliton in the literature. Now, the claim is also distinguished between two kinds of behaviors. So, of course, a necessary parameter to call something a soliton in a classical system is that it should be a localized solution. Okay? Now, this thing is definitely localized, extremely so. Don't forget these are exponentials. So it's a very nice and localized solution, which moves with uniform velocity. And it exhibits no distortion in its shape. And again, it's worth going back to our heuristic arguments in the beginning. Both the wave packet in the linear system was going to be distorted in shape because it's going to be expanding, and the other one, the non-linear part, was also getting distorted because it was being compressed and eventually reaching some kind of shockwave situation. So, but this one, which somehow you can think of as the balance between those two behaviors, exhibits, you can just look at it, it's a very simple, nice solution, and it does not, it can move without being distorted in shape. So this definitely has all of these properties, but one would like to also add one other condition, which I won't be able to really do justice today, but hopefully on Thursday, which is that colliding packets, and when I say packet, I mean something like a wave packet that you construct like that, need to retain the original shape velocity. So let me draw a little diagram here of what this behavior is about. So that means, number 2 means that, for instance, suppose you have 2 of these lumps of energy. I haven't discussed the energy yet, but we will do so in this end column. But of course, there's energy, which is energy density, which is concentrated here. So consider these 2 lumps, and suppose 2 are moving in opposite directions. What you want, in order for 2 to be satisfied, is that, okay, in the middle, you don't actually care, but asymptotically, what's going to happen is that these scatter through each other, and asymptotically, so far away, they have the original shapes and velocities that the original one had. If you're working in more than one dimension, you can actually allow things like phase shifts. So you might actually have a bit of a change in the phase and all that. Actually, possibly also here. But it definitely doesn't change its shape as they cross each other. And this is not the only kind of situation. You can also have situations where one of these is moving faster than the other one, so it catches up on it and continues. So this is basically something which, in an appropriate center of mass frame, you could sort of relate to that. But this is also a kind of behavior that you would like to have for this to be true. So if only one is satisfied, then one could call this a solitary wave. If 1 plus 2, then this is most, well, I'm not saying it's a generally accepted definition, but this would be closer to the strict definition of a soliton. And here I'm following, for this I'm following the book by, it's a standard book on solitons by Roger Rand. Okay, so this is these are the definitions, and that implies that solitons, if you want to be strict about it, are a subset of these solitary waves. So the question is, okay, we have many dynamical systems which are physically relevant, so which correspond to many different differential equations. How can we in general construct solitons like that? That's not going to be the topic of my lectures, but there are I just mentioned that there have been many techniques that have been developed specifically to find soliton solutions. Some of these go by fancy names like inverse scattering, Backlund transformations, and many others. And they can get quite technical, but they definitely have led to a relatively good understanding of solitonic solutions. But still, it's a difficult field. You're dealing with nonlinear equations, which are not always amenable to simple procedures like this. But the point of my lectures, which I guess, given a lack of time, I'll get to next time on Thursday, is that you can find the special cases of these kinds of configurations by also following topological argument. So by also looking at basically there's an interesting way of thinking of solitons as topological objects, which means that they actually interpolate between different topological sectors of a given theory. And I have not defined what topological sectors are, but I will do that next time. But for a given theory, you can have solitons that take basically between different vacua at x plus infinity and minus infinity. And because these sectors are topologically distinct, which means that there is no way to actually take your configuration and continuously deform it to a configuration which does not interpolate between two different vacua, then that guarantees the stability of these configurations. Okay, so that's one interesting point that we're going to get to. So basically, let me say the words. They connect different vacuum sectors. And the picture one should have in mind is, suppose you have a potential in your theory, and the potential has some vacua. Let's assume they're degenerate. So when I say vacua, I mean the ground states of the system, which you find by looking for solutions which do not depend on time. So they are static solutions, and they are minimizing the potential, so they have no kinetic energy, and they have also zero potential energy by choice of potential. So if you take those, you can think of these solitons as, so well, this is say phi1, phi2, phi3. These are different configurations of the fields. So this is the field, not X. This is actually the field. A soliton can be thought of as something which interpolates between two of these values. So at x equals minus infinity, it's this configuration. At x equals plus infinity, it's this configuration. And because these would in general, of course I'm not stating it here, be topologically distinct configurations, then there is no way to kind of unwrap that soliton and make it only, be at minus or plus infinity, leading to the same vacuum. So that is what this statement of connecting different vacuum sectors is trying to say. And we're going to focus next time on a particular class of these, which we will be finally calling BPS, which will have a special feature that can satisfy a given bound, and because of that particular bound that they satisfy, they are actually, in a way, linearizing the problem. So they admit linear superpositions of different solutions, which normally we don't. Sure? Yes. So instantons are very similar to solitons. Just instantons you think of in gauge theories in Euclidean space, and so basically you're not looking at finite energy because that concept is not so relevant for Euclidean space. You're looking at finite action solutions, but actually it's exactly the same. When you have different topological vacua, say in QCD, instantons are solitonic-like solutions which interpolate between those vacua. And the only difference is one is a dynamical situation. There is time here, and things move in time, while instantons work in Euclidean space, so there is no notion of time. That's why we call them instantons. So it's something that happens instantly. But definitely topologically, there are huge similarities between these two systems. Okay, I think I'm out of time, right? So then in the tutorial, we'll discuss another system, the Sand-Gordon equation, which has actually some of these true soliton solutions, and we'll give a few features of those with your input. Thanks.
Okay, so we'll start again at 1:15.